Hey guys, welcome back. We're still talking about triple integrals here, and this is a little bit different because now we're given a triple integral in Cartesian and we're asked to change it into cylindrical coordinates. So the integration we're given is from 0 to 1 with respect to y, 0 to the square root of 1 minus y squared with respect to x, and then the integral from x squared plus y squared to the square root of x squared plus y squared with respect to z. And so the very first thing that I think is important and something that's a good strategy for me is the fact that I just said that since z is our interior, these two equations that we have here are actually going to be equal to z. So likewise, if I keep going here, the middle integral is with respect to dx. So these two equations right here are going to be equal to x. And then the outer region, which is dy, is going to be equal to the equations for y. So that's getting a little busy up here. So what we're going to do is we're going to start writing stuff down and start figuring things out. And remember, we're going into cylindrical coordinates. So we need it in terms of r, theta, and z. All right. So the first thing we're going to do is look at these two equations. So I'm going to give you the square root of x squared plus y squared. And that's going to be equal to z. So when I square both sides, I get x squared plus y squared is equal to z squared. And then remember, guys, that x squared plus y squared is actually equal to r squared. And so that means that the upper bound for z is going to be r. So over here, I will do z, and the upper bound for z will be r. Well, we actually are okay with this because now let's look at the bottom one where we have an x squared plus y squared is equal to z. And just like before, we get that r squared is equal to z. Well, there we go. So our lower bound for z is going to be r squared. And that's pretty straightforward, right? That's what we can do for those problems. So then we have to start now looking at what I call the trace for what we're looking for bounds for the rest of these. So I'm going to go ahead and write down that y is going to be 1 and 0. And so that means that when we draw our trace, that y is going to be in between 1 and 0. So we're looking at the xy trace where y will be from 0 to 1. And we're going to use the equations of x equals 0 and x equals the square root of 1 minus y squared to graph the functions of that set trace. So we're going to take this equation right here and write down that this becomes x squared is equal to 1 minus y squared. And so we get that x squared plus y squared is equal to 1. But we want to be very, very careful about this when we draw our pictures. So let me go ahead and draw ourselves. No, didn't want that. Let me hold on for 1 second, guys. Let's draw like this. Okay, so I'm okay if there's no arrows on the other side. So the idea here is when we do our problems, we want the circle, but we want the positive of the x, right? So we want x is equal to the positive square root. So instead of actually having the entire circle, we want this region right here, right? So this is going to be x equals the square root of 1 minus y squared. But remembering that the actual equation for this is x squared plus y squared is equal to 1. And then we're only looking at where y is between 0 and 1. So we want this region right here. And this is all we want. So we're going to look at the fact that, again, going back to the equation we've been doing before, we get that r squared is equal to 1. So when we're looking at what's going on with our r, well, our lowest our r is going to be here is at 0. And then the largest it's going to be is actually at 1, right? The equation right here of 1. And then theta, because we're only looking at the right-hand side of the circle and the fact that we're specifically looking at when y is from 0 to 1, we're looking from 0 to pi over 2. So if for some reason we had given you the original bounds as -1 to 1, let's say hypothetically we did that, then this would change to -π/2. So that's the one thing we want to just stress there, is that that's what that would end up looking like. So when all is said and done, we're going to go ahead and write down that our overall integral now, well, we're only looking from 0 to π/2, and then we're going to use from 0 to 1. And again, we use what we call the trace, the xy trace for us. This is the y-axis, this is the x-axis, the xy trace to get these two outer bounds. And then we're going to look at our lowest z value, which is going to be r squared. And then our higher z value is going to be r. And then we're going to just simply write down the conversion factors for x, y, and z here. So x is equal to r cosine of theta, right? That's what the x would be. The y is going to be r sine of theta. Well, z is just z. And then we're going to add our special r, and then we're going to do dz, dr, d theta. Let me actually get rid of this little guy right here for a second so we don't get low. Okay, so this is the answer to our problem. You can simplify this down a little bit more if you want to and pull the r cubed out with the z and then do sine theta, cosine theta, but right now I'm okay with us leaving it right here. So there you go. Biggest suggestion made here is acknowledging what these equations are, and again, the outermost integrals are going to be the traces. That's going to help you guys with bounds for the other two. So hope this works for you guys, and we're going to come back in the next example and do exactly another one of these where we're going to go to spherical coordinates. So I'll see you guys in that next video. Take care.